Again, this time we'll talk again about the Hausdorff measure and the Hausdorff dimension, this time in relation to Hölder continuity and Lipschitz continuity. So let me first tell you what it is. Probably you've already heard of it, but let me write it down. So such a map F from Rn to Rm is Hölder continuous if so this just means that the modulus of f of x minus f of y is at most some constant times the modulus of x minus y to the alpha, and where alpha is bigger than 0 and at most 1. And now we have a special case which we call Lipschitz continuity. So this is just if it's Hölder continuous to alpha equal to 1. Okay, so that's the definition. You might have already seen it. So for Hausdorff measure and Hausdorff dimension, especially Lipschitz continuity will be important, but we will also cover Hölder continuity. So let's recall the definition of the Hausdorff measure. So this quantity here on the left-hand side is just this infimum over this series over the diameter of these ui's, where ui is a delta cover of the set F. So maybe let me write that F is some subset of Rn, and delta cover just means that the diameter of the set ui is at most delta and that this union covers F. Okay, so that's the definition. And now let's see what happens if we apply our map little f, or Hölder continuous map, to the set capital F. So by set theory we get, so this is basic set theory, that we get that this is in, well, let's say F of the union, and this is just the union of the F of ui. You have to be a little bit careful here. This holds for the union, but not for the intersection, but probably you know that. Okay, so what we can see immediately is that this union on the right-hand side is just a delta to the alpha cover of the image of F under the map F. So this is immediate because so here we have this for all values in the domain. Of course, the domain and the codomain don't have to be Rn and Rm, they could be also some subsets. And so that's that. And now let's see what happens to the Hausdorff measure. Oh, and I also forgot to mention, this of course is not yet the measure. So let me write it here. So the measure is the limit if we go to 0, and this quantity hs delta is non-decreasing, so this limit exists, and this defines our Hausdorff measure. But this is just a small reminder. We already saw a little bit about this last time. Okay, so now let's go on. What happens for the Hausdorff measure for the image? Okay, and what we want is we want to get an inequality. So let's see how we get it. So we look at these diameters of the images of the UI. So again, UI is a delta cover. And then, well, we apply Hölder continuity. We get that this is at most this series over the diameter of the UI to the alpha s. Let me write it by Hölder continuity. And so from there we get that the Hausdorff measure of the image is at most the Hausdorff measure, and now we have a different parameter. So here we have s, here we have alpha s of f. So let's see, how do we see this? So we take a so for small delta we take a union of ui's which are at most, say, epsilon away from the real value of this quantity, so of the Hausdorff measure, and then we see this is this is almost this thing here on the right hand side, and we see that we have some delta to the alpha cover for the image, and which gives a smaller value, so we get this inequality here by taking limits, respectively limits and infima. Okay, so that's our first inequality, and now let's see what we get for the dimension. So now we have an implication. So this inequality implies an implication. So let me write it clearly so that it's clear what I want to say. So from here we see that if this thing here is 0, then we get that also this, the Hausdorff dimension of the image is 0. So we get this implication. And now let's have a look at the dimension again. So the Hausdorff dimension of f was the infimum over the so this is over the non-negative real numbers, such that h s of f is equal to 0. So, or we could also take the supremum over the ones where it's infinite. So we have infinite Hausdorff measure. And this is equivalent, apart from maybe the case where we have dimension 0. There we have to be a little bit careful, but in general it's equivalent. So that means, so we have this implication, which means that the dimension of the image is at most 1 over alpha, the dimension of f. So we have that if this thing here is 0, so let's say if the dimension is alpha s, or we have something, let's say S prime bigger than alpha S. So let me write it down explicitly so that you know what I mean. Then we get that h of with the parameter S prime of f is 0, but this means, by what we have shown, that h of, then we have S prime divided by alpha of the image is 0, so that we get that the dimension of the image is at most 1 over alpha, the dimension of f. Okay, and now let's so if we set alpha to be 1, then of course we get that we have this inequality with a 1 here. So that's why the Lipschitz case is especially important. And now we can look at Bi-Lipschitz maps. So that are maps which we have, let's say, C1 modulus of x minus y is a lower bound for f of x minus f of y and the modulus of that. Then we have a second constant where we have this thing here. And these are especially important because they preserve the Hausdorff dimension by this inequality here. And so that's an important class to keep in mind for the Hausdorff dimension. And of course you can see immediately that Bi-Lipschitz maps are injective, so we have that if f of x is equal to f of y, then we have here a 0, we have here a 0, and then this also has to be 0. Of course the constants are positive, and then we get that x, oh well, we have just, oh, forget what I said, we have here at 0, so we get this has to be 0, and then x is equal to y. So this is an injective map, and so we also have an inverse map from the image to the domain, and so we also get the inverse inequality if we look at the inverse map which has the image as domain. Okay, so these are the dimension preserving maps, or maybe not the dimension preserving maps, but these maps preserve the dimension. And now let me give you another small fact which we will use in the next video. So namely, there's a fact about the dimension called countable stability. So this just means that the dimension of some countable union of some sets Fi is the supremum over the dimensions of the Fi's. And with that, we get that for f continuously differentiable, that the dimension of, so here f is just a function from the reals to the reals, that the dimension of the image is at most the dimension of f. And how do we see this? Well, that's if we know, so we look at, let's say, f restricted to minus n, from minus n to n, and well, as it's continuously differentiable and we have a compact interval, we get that it's Lipschitz continuous, so we get this inequality for all these restrictions, and then we just take the supremum and we still get inequality. So maybe to be more precise, we don't look at the restrictions, but we look at f and we look at the sets f intersection minus n to n. Okay, so that's it for today.